Hello everyone, welcome back to online lecture series on nanotechnology and surface engineering. Currently we have been discussing about the tools to characterize the nanoparticles, and we have completed many of the tools already. That is, we have completed X-ray diffraction, that is XRD, then scanning electron microscopy SEM, transmission electron microscopy TEM, and atomic force microscopy. We are only now left with ultraviolet or visible spectroscopy. So before going to that new topic, we will have a quick revision of our previous topics. First, we discussed about optical spectroscopy that uses the interaction of light with the matter as a function of either wavelength or energy to gain the information or details about the material. We have already discussed the fundamental or principle that is based on the Bragg's law, and it is purely based on the refraction of the light through this material or a specimen. Then these are the characteristics. The next topic was scanning electron microscopy. Here the basic principle is having specimen at the bottom and the electron gun at the top. In between we are having this anode, magnetic lens, the scanning coils, backscattered electron detector, and secondary electron detector. Here these three things, that is scanning coils, backscattered electron detector, and the secondary electron detector, these three are sending the signal to the TV scanner. Then the things which can be obtained with scanning electron microscopy are topography, morphology, composition, and crystalline structure of the material. There are three operation modes in this case. Primary, secondary, and tertiary. So this method is also having this is the another figure of the same method. Here at the top we are having electron gun, and at the bottom we are having this sample, and in between we have scan coils and the electron detectors. There are few advantages and disadvantages that are already we have in discussion. The next we studied about the transmission electron microscopy. Here we can obtain morphology, crystalline structure, and composition. So the arrangement is quite similar to scanning electron microscopy with few differences. In this case we are having the specimen in between. In our previous method the specimen was at the bottom. Here it is in between the condenser lens and objective aperture lens. Then we do have intermediate lens as well as projector lens. Here the basic principle is that the intensity of diffraction depends on the orientation of the planes of the atoms in the crystalline structure relative to the electron beam. Here also we discussed about few advantages and disadvantages of this method. Then we move to the atomic force microscopy, in which we are having a cantilever having a tip. So we get the signals from the short range forces between the tip and the sample. These forces are van der Waals, capillary, and electrostatic. So this is the tapping mode force. We discussed about the AFM components, like we are having this cantilever with a sharp tip. The sample is kept on the AFM sample stage, and laser is incident on this AFM cantilever and received by the 4th quadrant photodetector. This is the cantilever. The cantilever dimensions defines or determines how easy it will be to bend it. This is the image quality dependence on the tip size and shape. Then we are having contact mode AFM, in which there is a direct contact of tip with the specimen and the laser is incident and the detector is receiving the signal through the refraction. Here is the tapping mode AFM. In this case, we continuously tap this cantilever tip on this specimen through a piezoelectric material. In case of contact mode AFM, the feedback is deflection of cantilever, and in case of tapping mode, the feedback is oscillation amplitude. Now we will move forward to our today's topic, that is also the last topic of this chapter, that is known as UV visible spectroscopy. So let's begin. Here, this is the typical arrangement of ultraviolet or visible spectroscopy. As you can see, in between at the middle we are having the sample, and if we see on the right extreme side, then we have two different lamps. First is tungsten lamp and second is deuterium lamp. So here deuterium and tungsten lamps are used to provide illumination across the ultraviolet, visible and infrared electromagnetic spectrum. These spectra can be collected from samples as small as 60 to 100 microL using a microcell with a path length of 1 centimeter. So here, if we see, it provides UV. These two provides UV, then visible, and near infrared. So infrared, electromagnetic spectrum. So these two lamps do this task. They provide UV, visible and infrared electromagnetic spectrum. And then we are having a lens for the further processing. So all the rays passes through this lens, and we have a shutter which works as a standard shutter that it blocks as well as it provides a path to this rays through this sample. So here this spectroscopy is a technique used to quantify the light that is absorbed and scattered by a sample. So here we have two things, that light will be absorbed as well as some portion of light will be absorbed and some portion will be scattered. So here this quantity is known as extinction, which is defined as sum of absorbed and scattered light. So here, if I need to write down here, then here extinction which is equal to absorbed light plus scattered light. So this is the formula for this method. So here the light which is coming through this tungsten lamp and deuterium lamp via this lens will have two different possibilities. First it will be some portion will be absorbed and some portion will be scattered, and then again it passes through the lens. Then we have a slit, and through this slit we are having a grating, and here we have the element 1024 element diode array where it is being received. In its simplest form, a sample is placed between the light source and the photodetector. As you can see, the sample is arranged between the light source and the detector, photodetector, and the intensity of beam of ultraviolet or visible light is measured before and after passing through the sample. So here the intensity is measured two times. First is before passing through the sample, and second is after passing through the sample. And these measurements are compared at each wavelength to quantify the sample's wavelength dependent on the wavelength dependent extinction spectrum. So I hope you are getting this, that in this case the intensity of beam is measured before and after passing through this sample, and this measurement are compared at each wavelength so that we can quantify sample's wavelength dependent on the extinction spectrum. The data which is obtained here is typically plotted as extinction function of wavelength. Each spectrum is background correlated using a buffer blank so that it can be guaranteed that spectrum features from the buffer are not included in the sample extinction spectrum. Now the next point is the gold and silver plasmonic nanoparticles have optical properties that are sensitive to size. So in case of gold and silver nanoparticles, they are very sensitive to size. Then they are also sensitive to shape, concentration, agglomeration state, and refractive index near the nanoparticle surface, which makes the UV or visible spectroscopy a reliable or valuable tool for identifying, characterizing and studying the nanomaterials. So this is the advantage of visible spectroscopy. So kindly consider this as advantage. Then the measured spectrum can be compared to the predicted spectrum based on the numerical models. These numerical models are not part of your syllabus, so you don't need to go into much detail in numerical models. So here let me repeat this part, that measured spectrum can be compared to the predicted spectrum based on the numerical method, the numerical models. Non-plasmonic nanoparticles also have size and concentration dependent on optical properties. So here this gold and silver were plasmonic nanoparticles which have dependence on the size, shape, concentration, agglomeration state and refractive index. However, other which are non-plasmonic nanoparticles, they also have size and concentration dependent on the optical properties. However, their spectrum is not as sensitive to the dispersion properties such as in case of plasmonic properties. We have already discussed the last point that deuterium and tungsten lamps are used to provide illumination across the ultraviolet, visible, infrared and electromagnetic spectrum. Here the spectra can be collected from samples as small as 60 to 100 microL2 using the microcell with a path length of 1 centimeter. So that is the end of UV/visible spectroscopy as well as end of this entire chapter. So we have covered the last portion, that is ultraviolet or visible spectroscopy, in this lecture, and we have covered all the topics. So let me quickly go back to this and give you a brief idea of this. In this case, we have a tungsten and deuterium lamp working as a light source, which provides majority of the wavelength which is required. Then the light beam passes through this lens, and we have a shutter for permitting as well as preventing the light going into the sample. So with this help of this shutter, we can have the intensity before and after passing through the sample. So light will pass through this sample and then lens, and then we are having this slit, grating, and finally we have this array on which the light is received. And we have already discussed all these points. You can pause this video and make a note if you require. So that is the end of this chapter, that is tools to characterize nanomaterials. Thank you for watching this video.